this lesson's pretty much just about looking at the exponential function in general. Okay, so everyone's on page 171? Yeah? Perfect. Okay, so because this has a lot of reading involved, and I'm going to be talking a lot, could I have a volunteer to just read that first example for me, please? Thanks, Barney.
Mallory, a medical research scientist, discovered a new bacteria culture which could help strengthen a person's immune system. To find the growth rate, she isolated 5 cells of the culture and observed the following growth pattern. After 1 hour, there were 10 cells. After 2 hours, there were 20 cells. And after 3 hours, there were 40 cells.
Perfect. Okay, so what are you guys noticing about the cells? What's happening after every hour? Doubling. Good. Okay, so we started with 5 cells, and then every year after that it's doubling. Okay, so you could put that it's doubling. Okay, for part A, we have to let t represent the time in hours, and n of t represents the number of cells after t hours. The formula for n of t as a function of t is written as follows. Okay, so we have n of t is equal to a times b to the power of t. Okay, and a and b are constants, and a and b are also positive. We have to find the values of a and b and write the function. Okay, so to do that, we're going to use the function that's given. So n of t is equal to a times b to the power of t. Now, do you guys remember an exponent that would set the constant equal to 0, or sorry, equal to 1? So to the power of, I gave the answer. So if we raise anything to the power of 0, it equals 1. So why don't we sub in t is equal to 0 and we'll solve for a. Okay, so n of 0 will equal a times b to the power of 0. But as we just discussed, anything to the power of 0 is just 1. So we have something equals a. Where are we going to figure out what n at 0 is equal to? We're going to look at the table of values. Okay, when the time is 0, what's n at 0? 5. Okay, so our a is just 5. Now that we have a, we can solve for b. So again, n of t is equal to a times b to the power of t. But what did we find a to be? What does a equal? Equals 5. So we're going to sub that in. Just replace that a with a 5. Then we can look back at our table of values again, and we can plug in any time we want. I'm just going to pick t equals 1. So when we have t1, we have 5 times b to the power of 1. But what is n at 1? Okay, what's n at 1? 10. Hour. Okay, that's 10. So 10 equals 5 times b. And if we divide by 5, we get b equals 2. So as a function, we would have n of t equals equals 5. Our a value is 5. And our b value is 2, all to the power of t. Okay, and that's going from n of t equals a times b to the power of t. We've just now replaced our a and our b. Okay, so that's the function we're dealing with. We talked about how this is doubling. Okay, which letter do you think represents that we're doubling? B. Good. Okay, if you take a look at the table of values, what do you think 5 represented? Okay, the initial value or the starting value. For part B, we're going to use the formula to determine how many cells there were after 8 hours. Okay, so now that we have the function formula, we can just calculate, instead of t, we're going to plug in 8. Okay, after 8 hours, we're just going to find out what is n of 8. We we multiply 5 times 2 to the power of 8. And when we calculate that, what do you guys get? Good. So 1,280. And that's how many cells there are after 8 hours. Okay, so for the next one, they're asking, or they're telling us that after 12 hours, there's 20,480 cells. How many hours did it take to half that amount? So we could calculate it, or we could think about it. Every year, what's happening? It's doubling. So if we went back 1 year, what would happen? It would half. So if we had half of this amount, what year are we in? 11 years. So that's just a bit of common sense, and I'll show you just if you can't think like that, then how to solve for it. So we know that we need to figure out half of the cells that are there. So we have 10,240 cells. Okay, we're going to plug that into our formula. 5 is our A, 2 is our B, and we're going to figure out what T is. So Brett, this is just reviewing from yesterday. So to solve for the exponent, do you guys remember how to change the base? Okay, we're going to change the base, and then we're going to set the exponents equal to each other. So before we do that, let's get rid of this 5. So can you guys help me out? 10,240 divided by 5? Just shout it out as it comes. 2,048. Okay, so now we just need to play around and figure out, well, 2 to the power of what gives you 2,048? Is it by any chance 11? Okay, so if the base is the same, we can set the exponents equal. T equals 11. So you can think about it, or you can solve it. Either way.
Wait,
Hey.
no, it's not.
What happened?
I'm confused.
Go.
Like, oh, never mind. I see. No,
What were you confused
I
about?
answered my own question. I was forgetting that we already divided that 5.
Oh, okay. Yeah, we first divided by 5, and then we figured out 2 to the power of what gives you 2,048.
Yeah.
Okay, good. So if we were to actually graph, so y equals, you put in your y1, y equals 5 times 2 to the power of x. Go ahead, put that in your calculator. You will get a function that looks like this, and I want you to verify that. If you don't get something like that, then you're probably putting in your calculator incorrectly, and I want to help you. Do you want to borrow mine? Oh. Your button. So if we take a look at this graph, what is happening to the values? They're as we go further along the x-axis, what's happening to the y values? They're increasing. Okay, they're doubling each time, so they're exponentially growing. Okay, and hopefully you guys saw that it's called an exponential growth. Okay, so if I say it's exponentially growing, that means it's a growth. So we have another word problem. Need a volunteer out there, please? Bernie, thank you again. It's convenient because you're nice and close to the sound on this.
Chernobyl is a city in the former Soviet Union. In April 1986, there was a nuclear accident at the atmosphere. It was contaminated with quantities of a type of radioactive iodine. At the time of the explosion, the atmosphere was contaminated with 32,768 units of radioactive iodine. Following data was recorded for the dissipation of the radioactive iodine. After 1 week, there was 16,384 units left in the atmosphere. After 2 weeks, there was 8,192 units left in the atmosphere. After 3 weeks, there was 4,096 units left in the atmosphere.
Thank you. Okay, so we started with 32,768. After a week we had this amount, after another week we had this amount, after another week we had this amount. What are the amounts? What's happening to the amounts?
Halving.
Good, they're basically multiplied by half each time. So they're halving. Okay, so getting smaller by half. Okay, we could also say it's 2 times smaller each time. Okay, so if we had to put this into the function equation, where n of t equals 32,768 something to the power of t, what was that b value in the first example? 2. Why?
Double.
Because we're doubling each time. This time we're halving each time, so what's that b value going to be?
Half.
Oh, you guys are so smart. 1/2. Very good. Hey, and just noting again, this number right here, our a value, where's that coming from? The initial amount of iodine. Okay, so whatever you're starting with at 0 time, that's going to be your A. Okay, and then whatever is happening from week to week or month to month, year to year, okay, that is going to be your B value. So we're going to use this formula to determine how many units of radioactive iodine were left after 14 weeks. Okay, so what are we replacing T with? 14. So we have n of 14 equals 32,768 multiplied by, you can put a half or 0.5 to the power of 14. And when you calculate that, you should get 2. Okay, and we'll say 2 units. Isn't that crazy? We started with 32,768 and only after 14 weeks we're now at 2 units.
Is that even, is this factual?
Yeah, that's my question, like, is
Because
that
it's
even
still
accurate?
radioactive.
Because it is still,
Yeah.
I actually don't know if that's truth or
You
not.
can't go there, still.
So if it is decreasing that much, we actually say this is called a decay. Okay, so exponentially it's getting smaller and smaller and smaller that quick. So it sounds like it's a false example. But in this case, I just want to point out, if your B value, your B parameter, is between 0 and 1, you're going to have a decay. And what does a decay look like? Well, let's check it out. Okay, so we're going to put this equation, n of t, or y equals 32,768 times 0.5 to the power of x. Okay, let's put that in our calculator. I'll graph this one with you. You're probably going to notice that it's not working, and you're going to have to change your window. Okay, so we'll put 32,000.
I'll give you that, that's right. I'll give you oh.
Okay, so when I graph that, I'm going to get nothing. So luckily our workbook is generous, and they're telling us, oh, maybe let's change our window settings so that we can see this graph. You guys remember telling me that the initial amount was 32,768? So where do you think on the y-axis that's going to be? When x is 0, or your time is 0, where are we at? All the way up there. So we've got to change our window settings.
Easy.
And we're going to go -1, x max 8, y min -30,000, y max 64,000, and we don't want to go by a scale of 1, we'll go by a scale of 10,000. So don't be shy changing that scale. Okay, taking a look at the function, what's happening? It's decaying, or we could say that it's exponentially falling, it's getting smaller and smaller and smaller. Do you guys see it passing the x-axis? No, is it touching the x-axis? It looks like it might be, but it's actually not. It's just getting smaller and smaller and smaller, closer and closer and closer, but it's never actually going to cross the x-axis. Okay, so whenever the graph is getting smaller and approaching the x-axis, we call that a decay. Did anyone have trouble graphing that? Okay. So moving on. The exponential function is represented by y equals a times b to the power of x. Now in the last class, one of the students asked, okay, well a can't be 0, which makes sense because 0 times anything is 0. So we wouldn't have an equation if it was just 0. Okay, and they're saying that b has to be greater than 0. So, and b can't equal 1. Why can't b be negative? Okay, I'll help you. So b is basically describing whether you're growing or you're decaying. So a growth factor would be like multiplying exponentially by 2, 3, 4. Okay, and a decay would be any value between 0 and 1. So that's like halving, or taking a quarter or an eighth. So it's getting smaller. If you were to take a negative, you can't take a negative of, say, 1 unit of iodine, right? Okay, it's either a unit or it's part of a unit. It's not a negative unit. So you can't really take negative units. Okay, you either have them or you run out of them. But in the example of exponential growth and decay, you're getting very close to running out of them, but never actually do. Okay, so b can't be negative because you can't have negative of something. All right, so we're going to compare two graphs, and it's pretty much exactly what we just looked at. We had a growth factor of 2 or a decay factor of 1/2, but we're going to talk a little bit more about the features of these graphs. Okay, so without using our calculator, we're just going to fill in this table of values. The first one we're looking at is y equals 2 to the power of x. Okay, so in this one, we're just going to take these x coordinates, and typically when you create a table of values, you want to go from x is -3 to x is +3. In this case, they're taking us one further, which is alright, but we're just going to sum in. So y equals 2 to the power of -3. This is review from yesterday. So 1 over 2 to the power of +3 is actually 1 over 8. Okay, we're taking the negative exponent, we're making it positive, and then 2 to the power of 3 is 8, so 1 over 8. Okay, let's try 2 to the power of -2. So that's like 1 over 2 to the power of 2, which is 1 over 4. How are we doing? Okay, what about 2 to the power of -1? It's like 1 over 2 to the power of 1. We have 1/2. What's 2 to the power of 0? Anything to the power of 0 is? 1. Good. Okay, what's 2 to the power of 1? 2. 2 to the power of 2? 2 to the power of 3? 2 to the power of 4? 16. Awesome. Okay, how about we plot these points? Okay, so I'm just going to start at 0. So we have 0, 1, 1, 2, 2, 4, 3, 8, and then 4, 16, which will be off the grid. Then I've got to do these little itty bitty ones. So -1 we have 1/2, -2 we have 1/4, -3 we have 1/8. Can you guess if we had -4, x is -4? Instead of 1/8, next one would be 1/16, then 1/32, 1/64, so on, so on, so on. So it's going to keep getting smaller and smaller. It's going to eventually approach the x-axis. It's not going to cross or touch it though. Okay, let's just draw a line through our points here. And we're going to jump to the table of values at the bottom. So specifically with y equals 2 to the power of x, what is the domain of this function? We're looking at the x values. Are there any restrictions going left or going right? No, so what's your domain?
All real.
X is an element of all real numbers. Okay, what about your range? Is it going to go to infinity?
Yeah.
Okay, what about as we go down this way? Hey, is it going to touch 0 though? So greater than 0, yeah. So y is greater than 0. If we do not touch y equals 0, is there an x-intercept? No. What's your y-intercept? 1. Okay, when x is 0, y is 1. Now, just a bit of review from last year, we introduced the concept of an asymptote. Asymptote is basically a line where the graph or the function is going to approach this line, but it's never going to actually touch it. So it's just the equation of the line where the graph is approaching. So if we had to look, this graph is approaching the line of the x-axis. The equation of the x-axis is y equals 0. So the equation of our asymptote is y equals 0. Okay, so the equation of the line where the graph is approaching is the x-axis, which is y equals 0. Okay, I'm just going to shoot back up to a here. So it's asking us to state the values of a and b. Let's just talk about this one first. So for y equals 2 to the power of x, what's your a value? Okay, if we're starting with y equals a and b to the power of x, we have 2 to the power of x. What's in front?
1.
Okay, a is 1. What's your b? 2. Do you guys think there's any correlation between a is 1 and maybe your y-intercept? Maybe. We'll investigate. There's a few examples we'll talk about later, but it might have something to do with it. Okay, and as you can see, our b value is our growth factor, so increasing by 2 each time. Okay, you're multiplying by 2 every time. Okay, let's take a look at half to the power of x. I'm going to give you guys a minute. We went through this one together. I want you to figure out what are the values in this table of values. So you're subbing in x coordinates into this equation. So a half to the power of negative 3. Half to the power of negative 2. Question for you. What do you do? What do you guys notice on the table of values? Okay, so see how there's a line here? You're going to plug into the value for x. And so you have half to the power of negative 3. And you put another one. You just have to plug that in. Yeah. Just let them sit there. You just like this is one. Why is it on the bottom? Okay, to use brackets. And 1 divided by 1 over h basically. Is just h. Do you have that? Okay, so what are you guys noticing about the table of values of half to the power of x compared to 2 to the power of x? What's happening to the values? Basically, opposite, right? Okay, so if I go half to the power of -3, we get 8. Okay, half to the power of -2, 4. Half to the power of -1, 2, 1, half, quarter, and 8, 1/16. Okay, and truthfully, if you calculate that first one and you know it's an 8, what's happening each time? It's halving. So half of 8 is 4, half of 4 is 2, half of 2 is 1, half of 1 is half. Okay, so you could plug it in every time, or you could just think about what that value means. Okay, but we're just learning, so that's okay. Now let's plot these points. We have -3, 8. So 1, 2, 3 of 8. Okay, -2, 4. -1, 2. 0, 1. 1 1/2. 2 1/4. 3 and 8. 4, 1/16. Connect the dots, and you can see that the numbers are exponentially decaying or falling. Okay, always good if you're plotting more than one graph, just make sure you label it. So let's talk now about the red graph, the graph of y equals 1/2 to the power of x. What is the domain?
All real numbers.
Okay, x is an element of all real numbers. Very good. Okay, how about the range? Is it approaching a certain line? Good, it's approaching that x-axis again, so y is greater than 0. Okay, do you have any x-intercepts if it's not crossing the x-axis? No x-intercepts. Good. How about the y-intercept? 1. Good. You guys are filling in the table as we're talking, right? Good. And then the equation of the asymptote?
Y equals 0.
Y equals 0. So, any of that information different? No, it's all the same. Okay, looking at part A again. Okay, y is equal to 1/2 to the power of x. What's your A value? And what's your B value? 1/2. Okay, what's your y-intercept? 1. Good. For part E, 2 to the power of x, we've said it a few times, it's a growth function, and 1/2 to the power of x is a decay function. So because we've talked a little bit about our B value already, I'm going to save us a bit of time, and we're not going to graph all of these. We're just going to talk about them, okay? So just note on all of these examples, your A value is 1, and we're just looking at B. Okay, so if I have y equals 3 to the power of x, just take a guess, growth or decay? Growth. Okay, good, growth. Okay, growth or decay? Growth. Decay. Decay. Okay, if I were to graph, say, y equals 3x, it'd look like this, and we'd go through 1. Okay, because our A is 1. If I were to graph this, it'd just be pretty much the reflection in the y-axis. Again, y-intercept 1. What's going to grow more rapidly? B value of 3 or B value of 10? 10. So if I were to graph this one, okay, it'd just be a little bit steeper. Okay, and this one would be decaying at a steeper incline as well. Okay, what do you notice about the y-intercept on all of them? All the same because your A is 1. Okay. So let's just talk about a few of these effects. So if B is greater than 1, the curve rises more sharply as B increases. Okay, so we talked about that already. If B is a greater value, it's going to increase sharply. Okay, so it's going to have a steeper inclined than it would if it was a 3. Okay, when we have a value of b between 0 and 1, the curve falls more sharply as b decreases. Okay, so 1/10 is a smaller number than 1/3. It's going to decrease more sharply than the 1/3. So without using your calculator, we're just going to draw a little sketch. 5 to the power of x. Growth or decay? Growth. So our function will be increasing. And 0.2 to the power of x is between 0 and 1, so we have a decay. Part E, it's asking about the x-intercepts. Do we have any? Is it crossing that x-axis? No. Okay, so no x-intercepts. Part F, it says state the y-intercept of each. What's the y-intercept? Okay, no, the y-intercept would be 1. Okay, and if we're talking about y equals b to the power of x, if a is 1, this is what we have, right? If we're trying to find our y-intercept, all we have to do is set x equal to 0. Anything to the power of 0 is? 1. Oh, you guys are awesome. Okay, so our y-intercept is 1. Okay, lastly, domain. Or not lastly, but what's the domain? All real numbers, good. And the range? Greater than 0. And the asymptote? Y is equal to 0. Perfect. So on the next page, we're going to be looking at how the a value impacts your graph. So we've seen a few examples of this already, but now we're just going to check it. So taking a look here, we have 3 to the power of x as our original function. Okay, as you can notice, with all of the other graphs, there's still 3 to the power of x, 3 to the power of x, 3 to the power of x, but the a value has changed. This one has an a value of 1, so 2, 5, 0.5. So what's going to happen, maybe you can just watch along. If you graphed it, you would observe this too, but if you put 3 to the power of x in there, remember we talked about that y-intercept? You replace x with 0, and the y-intercept would be 1. Okay, so 3 to the power of x is going to go through y equals 1. This will be the general shape. What's going to happen to the y-intercept when we look at this one though? We have y equals 2 times 3 to the power of 0. We get 2. So instead of going through here, we're now at 2. Okay, still going to approach 0, but it's got to go through a different y-intercept. It's growing at the same exponential rate, just now it's multiplied by 2. Okay, next one. Any guesses what the y-intercept might be? 5, very good. Okay, should probably label these. Y is equal to 3x. Y is equal to 2 times 3 to the power of x. Next one, again, if we subbed in 0 for x, we would get our y-intercept of 5. Okay, so 2, 3, 4, 5. Still going to approach 0, but we're going through a different y-intercept. Okay, and what's the y-intercept of the last one? 0.5, good. Okay, so this one's going to go through half on the y-axis. So I think we can conclude that the a value is your y-intercept. Okay, do we really need to fill in this table? Okay, I think we've talked about it. So for part C, basically we figured out that a describes your y-intercept But also, what has happened to the graph? Like, what's happened to those y values? I'll just put you back here. Okay, the original graph was going through y equals 1. Let's just look at y equals 5 times 3 to the power of x. What's happened to the y coordinate? It's multiplied by 5. So could we say that it's a vertical stretch? Absolutely. Our a and our b actually relate very similarly to the transformation unit that we looked at before. Okay, so if a is our stretch factor of 5, that means all the y coordinates are going to be increasing by a factor of 5. Okay, if our a is a half, we multiply all our y coordinates by a half. Okay, so another thing that we can say about our parameter a is that it's a vertical stretch factor. Okay, moving on to part D. This is a bit of review from Unit 1, dealing with function notation. Telling us that the function is 3 to the power of x. So in function notation, part 1, I would say y equals f of x. Part 2 is y equals 2 times f of x. Okay, Jackson, what would be part 3?
Y equals 5.
Perfect. Okay, and then the last one, y equals 0.5 times f of x. Now you have your unit test coming up on Friday, so the value that's in front of the function, what parameter is that? Or what does that parameter do in front of the function? Vertical stretch about the x-axis by whatever a is equal to. Okay, so that's basically part E. Okay, vertical stretch. It's about the x-axis by a factor of a. Okay, which pretty much we've talked about in part F. Looking at the y-intercept, we've also already talked about that. Okay, so A is pretty much your y-intercept. How are you guys feeling so far? So if you're to study this lesson, this next page is pretty much a fill in the blank. And after we fill it in, it's going to be really a handy tool for you to come back to if you're studying for a test and don't have much time. Alright, so looking at the equation y equals a times b to the power of x. Okay, what is the y-intercept? A. Good. Okay, so our y-intercept is always the a value. Okay, is there an x-intercept? No, there is no x-intercept. Okay, what did we refer to the x-axis as?
Asymptote.
What kind of asymptote?
Horizontal.
Awesome. Horizontal asymptote. Okay, what's the domain of an exponential function? Draw a little picture if you need.
Yeah, all real.
X is the element of all real numbers. And the general range?
Greater than 0.
Y is greater than 0. Don't put that equal sign because it will never equal the x-axis. Okay, when a is positive, for when a is positive, when b is greater than 1, what kind of function? Growth, good. And when b is between 1 and 0, the function represents a decay function. If we have a growth function, that means that when b is greater than 1, the curve rises sharply as b increases. So the greater the b value is, the sharper the curve will be. Or the steeper the curve will be. Okay, when b is between 0 and 1, the curve will fall sharply. So the smaller the b value between 0 and 1, the steeper it falls. Okay, and the last summary is dealing with the a parameter. When a is greater than 1, we have a stretch. Okay, say if a was 3, are we going to have a compression or an expansion? Expansion, good. When a is a fraction between 0 and 1, do we have an expansion or compression? Compression, good. Now this is review of, again, our last unit. So if we have y equals negative a bx, okay, maybe I'll give an example. Negative 2 times 3 to the power of x. Okay, what happens when a is negative? Reflects over the x-axis. Okay, good. Okay, another thing, if you wanted for the growth, you could just draw a little picture that it's growing, and for decay, you could draw a picture that it's decaying. A few more questions. So let's describe how the graph of the second function compares to the graph of the first. And this is pretty much, now that we've learned about exponential functions, it's a review of the transformations unit. Okay, so our original function is 4 to the power of x. We've got to think about all our transformations, so vertical stretches, horizontal stretches, reflections, and then vertical and horizontal translations, and decide what's happening. So I'll give you a minute to think about it. What was that, Booker?
Stretch by 2.
What kind of stretch?
Horizontal by the y, or vertical by the x.
So it is a vertical stretch, okay, it's outside the function. Okay, vertical stretch by a factor
2.
of 2, and it's about the x-axis. And there's one more transformation. Instead of x, we have x minus 2. So we have a horizontal translation, and we're going right 2 spaces. Next one, we're starting with y equals 2 to the power of x, and the result is y plus 4 equals negative 2 to the power of x divided by 5. Let me rewrite this one. By moving the 4 to the right hand side, we get y equals negative 2, 1 over 5x, and then minus 4. Okay, so we started with 2 to the power of x, now we have a negative in front. So if we have a negative in front, what are we reflecting over? The x or the y-axis? What values are changing? The y-coordinates or the x-coordinates? Okay. If this was actually a negative 2 inside, they would have had brackets like this. Okay? So the negative's on the outside. So if the negative's on the outside, what's changing? The y-coordinates or the x-coordinates? Y-coordinates. So we're reflecting over x-axis. Good. Reflection over x-axis. Okay, what does the 1/5 of x tell us? We had to the power of x before, now we have 1/5 times x. What do you think it is, Bernie?
A compression, like a stretch.
Okay, so horizontal stretch, and what do we have to remember with the b value?
Oh, it's
The reciprocal.
reciprocal.
Okay, so horizontal stretch, by a factor of 5. Okay, and that's about the y-axis. And then lastly, what does that negative 4 tell us? Down 4, awesome. Okay, that's a vertical translation, down 4 units. Okay, that stuff's got to be 100% because we have a unit test on Friday. Alright, next one. Explain using transformations why the graph of y equals a third to the power of x is a reflection in the y-axis of the graph y equals 3 to the power of x. So this is the graph we're starting with, and y equals 1/3 of x is the graph we're ending with. How can we explain that that was a reflection in the y-axis? What did we learn yesterday about negative exponents? If I change the 1/3 to a 3, that means I need to have a -1 exponent. Okay. So 1/3 to the power of 1 can be changed to 3 to the power of -1, and that's all raised to x. Power of a power, multiply the exponents, and now we have 3 to the power of -x. If x went from positive x to negative x, that should tell us that because the x coordinates are changing, we're reflecting over the y-axis. How's that? Yeah? Okay. The very last question. So we're not allowed to use a calculator. This is pretty much a review of everything we talked about today, and it throws in a bit of transformations too. Okay, so we have the function 4 to the power of x plus 2 minus 6. We have to figure out the domain and range of that. We need to figure out the y-intercept, and we need to figure out any horizontal asymptotes. So do you guys want me to start with the hint? I would first graph, without using a calculator, y equals 4 to the power of x. So let's just do that. What do you guys remember? What's your a value? 1. So what's your y-intercept? 1. Okay. What's your horizontal asymptote? X equals, or the x-axis, which is y equals 0. And that's going to increase sharply by a growth factor of 4. So that's your starting point. Now you need to use transformations to move the graph. Okay, so I'll just give you a minute to do that. Think about what does the x plus 2 do to 4 to the power of x? And what does the negative 6 do? So Xander, what are the transformations? Okay, so you're going down 6 and left 2. Perfect. Okay, so if our y-intercept was at 1, where's our new y-intercept? We go down 5, right? Okay, and I'm just talking about the down 6 right now. So we're going to go down 6 spaces. It would be at negative 5. Okay, so it would be like this. But keep in mind, our y-intercept before was 1, but we're approaching y equals 0, right? So if we're moving the graph down 6, where's our new asymptote? It was at 0, now down 6, negative 6. Okay, so we've actually answered part C first. Just just by moving the graph down, we figured out that the equation of the asymptote is y equals -6. Okay, have we also figured out the range? The range is y is greater than -6. Regardless of whether we move this graph up or down, left or right, will the domain change? No, it's still going to be x as an element of all real numbers. Now we need to figure out the y-intercept. So who thinks it's -5? Okay, one does. Okay, it was at, if I just moved it down 6, it would be at -5, but I also need to shift the graph left 2 spaces. So that means something up here is going to affect it, okay? So to solve for this, all we have to remember is that we let x equals 0, we plug that into our function, and then we solve. Okay, so we plug in y equals 4 to the power of 0 plus 2, and then we subtract 6. 4 squared is 16. 16 minus 6, we get a y-intercept of 10. So when we move this graph over, keep in mind it's rising exponentially. So obviously it really rose up to 10. Okay, so your y-intercept is 0, 10.